Hello everyone, welcome to Concepts in Chemistry YouTube channel. So today in this video we will be discussing on more questions in multiple select questions series or MSQ series. So yeah, we already uploaded two videos and we discussed there two questions. So you will find somewhere the I button. Yeah, you can click the I button to see those videos or those questions. Yeah, these questions will be very important for upcoming competitive exam like CSIR-NET, GATE, BARC or IIT-JAM. But since this MSQ type questions we usually see in GATE and IIT-JAM exam, so for that purpose we can say this type of questions or this series of questions will be special for GATE and IIT-JAM aspirants. So yeah, let's start the questions without any delay. So yeah, so MSQ question number 3. So yeah, the questions in this three statements are given, so we have to find the correct statement from the above three statements. So the statement 1 is the CO carbonyl stressing frequency of the following compounds is in the order. So 3 organometallic complex are given and they mention the CO stretching frequency will be in the order like this order. So in this complex the CO stretching frequency will be higher than this complex and this CO frequency will be higher than this complex. Statement 2 is CO4, that is cobalt, this is also a cobalt carbonyl complex, is less Bronsted acid than this complex. So the statement third statement is the geometry of nickel tetracyano 4- is tetrahedral rather than square planar. So three statement, one is regarding the carbonyl stretching frequency of organometallic complex, the second one is regarding the Bronsted acidity of some organometallic complex, and the third one is the geometry of the nickel tetracyano 4- complex. So the correct statement from the above we have to find the correct statements from the above three statements. So yeah, we will discuss every statement in details step by step. So yeah, let's discuss the answer with details. So yeah, this cobalt carbonyl complex with SiX3 kind of ligand, SiX3 kind of ligand is given 4 carbonyl complex, C 4 carbonyl ligand and 1 SiX3 kind of ligand. X is here hydrogen, fluoride and chlorine. See the questions. If SiX3 we can write like SiX3, X is hydrogen, chlorine, fluorine for 3 cases. So yeah, consider this complex and please listen carefully and you can also note down in your copy. So we all know that the electronegativity order of this hydrogen, fluorine and chlorine is in the order. Fluorine is more electronegative, chlorine is less than, the least electronegative is hydrogen among the given 3 atom. So if we consider this electronegativity, then we can say that positive charge density over silicon center. So since fluorine is more electronegative, fluorine accept or attract electron density from silicon d orbital. So we can say that positive charge density over silicon center will be in the order. So in fluorine case, the positive charge density over silicon center is more because fluorine substituent is attached with silicon. Fluorine 3 fluorine atom attract more electron density from silicon center. So we can say the positive charge density over silicon center will be in the order. More positive charge density will be in the more positive charge density on silicon center will be in case of SiF3 and less positive charge density in case of SiH3 because H is less electronegative than fluorine. Now pi acceptance ability, from this observation we can say that pi acceptance ability of the whole group. Now from electronegativity we obtain a conclusion like the positive charge density of our silicon metal is most for SiF3. Now we can say the pi acceptance ability of this whole group SiX3. SiX3 means in this case X is fluorine and chlorine. So now pi acceptance ability of this whole group we can say will be in the order SiF3. This whole group is more pi acceptor. So among this SiH3, SiCl3, SiF3, this group is more pi acceptor, behave as a more pi acceptor, means it accept electron density more from metal center. So that's why we can say that SiF3 is more pi acceptor, or SiF3 behaves as a more pi acceptor ligand than SiCl3 than SiH3. Now pi donor ability of metal cobalt towards the CO ligands. So if we consider the pi donor ability of this cobalt, towards this CO ligand, then we can say since SiF3, just consider in place of X F3, since SiF3 is more pi acceptor ligand, or SiX3, or SiX3 means in this case SiF3 is behave as a more pi acceptor ligand in this case, or pi acceptor group, it will accept more electron density from cobalt toward itself. This SiF3 is more pi accepting in this case, behave as a more pi accepting group. That's why it will accept more electron density from cobalt center. That's why this cobalt center will donate less electron density towards the carbonyl group, towards the pi star orbital of the carbonyl or CO group. That's why I have written here pi donor ability of metal cobalt center towards CO ligands. So pi donor ability of cobalt center towards CO ligand is highest for SiH3, because if we consider SiH3 here, SiH3 is less pi accepting among these three group, SiH3, SiF3, SiCl3. It will accept less electron density from cobalt metal center. That's why cobalt metal center will donate more electron density towards the CO ligand. Since SiF3 is more electronegative in this case, and SiF3 whole group behaves as a more pi accepting group, that's why it accepts more electron density from the cobalt metal. That's why for this SiF3 case, cobalt center will donate less amount of electron towards the pi star of this CO ligand. So that's why I have written here pi donor ability of metal cobalt towards CO ligand is in the order. So for SiH3, the cobalt metal center donates maximum amount of pi electron towards the pi star orbital of CO, and in SiF3 case, the cobalt center donate less electron density towards the pi star orbital of the CO ligands. Now we can interpret from these observations electron density of pi star orbital of CO. Now for SiF3, since cobalt metal center donate less amount of electron towards the CO ligands, or you can say cobalt metal center will donate less amount of electron towards the pi star orbital of the CO ligand. That's why we can say electron density of pi star orbital of CO ligand will be in the order. So electron density in the pi star orbital of the CO ligand will be highest for SiH3 and lowest for SiF3. Since SiF3 attract more electron density toward itself from the metal center, that's why metal center donate less amount of electron density towards the pi star orbital of the CO ligand. And since SiH3 is less pi accepting, it will accept less amount of electron from cobalt center. That's why cobalt center donates more electron density toward the pi star orbital of the CO ligand. So that's why we can say that since there is more amount of pi star, there is more amount of electron density. There is more electron density in the pi star orbital of CO in case of SiH3. That's why we can say the bond order of the CO will be in the order in this case. So more electron in pi star orbital means less bond order. weak bond. More electron in pi star means the bond order become less and bond become weak. So in the case of SiF3CO whole CO4, in this case there is less amount of electron density in the pi star orbital of CO. That's why the bond order of cobalt, the bond order of CO carbonyl frequency in this cobalt complex is more, because in this case cobalt metal center will donate less electron density towards the pi star orbital of the carbonyl ligand. Because of this, more pi accepting group attached with the cobalt. In this case, this is less pi accepting, this will accept less electron density, and cobalt will donate more electron density towards the pi star orbital of the carbonyl ligand. That's why for this case the bond order become less. For SiF3 case the bond order become high. Whose bond order? Bond order of the carbonyl. Bond order of the carbonyl. We all know, since bond order of the carbonyl is highest for this complex, so we can say the nu bar CO means the frequency of CO, stretching frequency of CO molecule will be highest for this case and lowest for this case. So the stretching frequency, carbonyl stretching frequency of the of the three complex will be in the order. So SiF3 CO cobalt CO whole 4, in this case the carbonyl stretching frequency will be most, and in SiH3 in this case the CO stretching frequency will be least. Simple things, SiH3 less pi accepting, it will accept less electron density from cobalt metal center. Cobalt metal center will donate more electron density towards the pi star orbital of the CO or carbonyl ligand. More electron density in the pi star ligand, the bond order become less. Bond order become less means bond become weak. SiF3 accepts or attract more electron density from the cobalt metal center towards itself. Cobalt metal center donates less electron density towards the pi star orbital of the CO or carbonyl ligand. Since there is less electron density in the pi star orbital of the CO ligand, in this case the bond order become more and the nu bar frequency also become highest for this complex. I hope this all these discussions or all these observations, all this point you can make a note, and please this is a simple thing. I hope you guys already understood what I am trying to say. Just more pi accepting SiX3 group, it will accept more electron density towards itself. Cobalt metal center donate less electron density towards the pi star orbital of the CO ligand. Less electron density in the pi star orbital means more bond order, that's indirectly becomes nu bar CO more. So for SiF3, since it is more pi acceptance, it will accept more pi electron from cobalt. Cobalt will donate less electron density towards the pi star orbital of the CO ligand. That's why for SiF3 case the bond order of the CO become greater, and that's why the nu bar CO or stretching frequency of CO become highest for SiF3 case. Yeah, so the CO stretching frequency of the following compounds is in the order. So yeah, the order is correct order. The CO stretching frequency will be in the order, or they give the order and we just discussed in details. So the order should be this: SiF3, the CO stretching frequency is most for SiF3 case and least for SiH3 case. Now second is the Bronsted acidity of these two carbonyl organometallic complexes. So Bronsted acidity means we have to consider the conjugate base acidity. So conjugate base more stable means this equilibrium shifted to the right side means more H plus will release this complex. This anion is more stable. This anion is more stable means conjugate base. This H plus will form more and more. This equilibrium shifted to the right side. If this after deprotonation, this is the mother conjugate acid, we can say mother conjugate acid. This is the conjugate base. After removing H plus, if this anion or this conjugate base is more stable, then this equilibrium shifted to the right side or more H plus will form. That's why we can say if the conjugate base is more stable, then that mother conjugate acid will be more acidic. If conjugate base is less stable, then the mother conjugate acid will be less acidic. That is the main theory of Bronsted acidity. So two organometallic complex is given. One is C cobalt carbonyl, one is cobalt trimethyl phosphine. So yeah, if we see the equilibrium of the deprotonation of this complex, this is conjugate base after deprotonation H plus. This is the second one. So we have to compare the stability of these two conjugate bases. Among these, the more will be the stable of the conjugate base. That conjugate base is more stable, and the conjugate acid of that conjugate base will be more acidic. More stable the conjugate base, this equilibrium shifted to the right side means more deprotonation take place, more H plus will form, and that becomes more acidic. So more stable the conjugate base, the mother conjugate acid will be more acidic. Less stable the conjugate base, the mother conjugate acid will be less acidic. This is the fundamental theory of Bronsted acidity. So yeah, now A and B is the conjugate base of acid, or you can say complex 1 and complex 2. Now we have to consider the stability of these two complex. So yeah, in the both complex, uni negative means on negative charge is there. So in both complex are uni negative, on negative charge is there. Now we all know that the more the ligand is pi acidic or pi accepting, it will attract more electron density from the metal center. So in this case, CO carbonyl and trimethyl phosphine. So yeah, trimethyl phosphine 4. So 4 trimethyl phosphine is there. Now CO, we all know CO is more pi acidic than PME3. So carbonyl group is more pi acidic than trimethyl phosphine. So carbonyl will accept more electron density from the metal center. We all know, just like previous case. More the ligand is pi acceptor or pi acidic, it will attract more electron density toward itself from the metal center. So due to greater pi acceptance, now since CO accepting more ligand from the metal center, due to greater pi acceptance, the CO cobalt and carbonyl bond become stronger. So CO, this carbonyl group accepting more electron density towards itself from the metal center. Since it will accept more electron from the metal center, the bond between cobalt and carbonyl become stronger. The bond order become more. Since PME3 accepts less electron density from cobalt metal center, the bond become cobalt and PME3, or you can say cobalt and phosphorus. In this case, cobalt and carbonyl, carbon of the carbonyl compound, cobalt and the bond between the carbon of carbonyl compound. In this case, the bond between cobalt and the phosphorus atom of the PME3 ligand. So since carbonyl accepts more electron density, it attracts more electron density from the metal center, the bond between the cobalt and carbonyl group become more stable. The bond order become more. We all know this kind of things. Since PME3 attracts less electron density from cobalt metal center, the bond between cobalt and PME3 is not so much stronger as CO carbonyl whole 4. So due to the greater pi acceptance of carbonyl group, the cobalt CO bond becomes stronger than cobalt PME3 bond. So we can say, this conjugate base, so the negative charge is on the cobalt metal center. That's why CO group accepts more electron density toward itself. The CO and the cobalt carbonyl group bond become more stable. In this case, cobalt PME3 bond become less stable. So we can say that A is the conjugate base of 1 A, that is conjugate base of 1, is more thermodynamically stable. Since the bond between the cobalt and the ligand, the bond between the metal center and ligand is more stronger, means that complex should be thermodynamically more stable. The bond between metal center and the ligand, is weak, or you can say, yeah, weak. So we can say that's the stability, thermodynamic stability of the complex is less. So this is a simple thermodynamic criteria. The bond between metal and ligand, is stronger, means this whole complex is thermodynamically more stable. So A is thermodynamically more stable than B. So we can say A, that is conjugate base of 1, is thermodynamically more stable than B, which is conjugate base of 2. So since A is more stable, this is a conjugate base of 1, this is more stable, that's why we can say this compound's 1 is more bronze-state acidic than B. A is more stable, this compound will form this base more and more by releasing H plus. This is less stable, so the prone towards H plus formation or deprotonation is less for this compound. So the conclusion is that since the conjugate base A is more stable than conjugate base of B, so the one, so conjugate so A is conjugate base of 1 and conjugate base A is more stable, that's why 1 is more bronze-state acidic than 2. So A is CO, cobalt carbonyl whole 4, B has stronger bronze-state acid than A is CO PME3 whole 4. So I think you you got the point. So the stability, how can we measure the stability? Just the electron accepting power of the ligand. CO is more pi accepting ligand than PME3. CO abstract more electron density from cobalt center. That's why cobalt CO bond become more stronger. More stronger bond between metal and ligand means that complex is thermodynamically more stable. So that is the theory behind the stability of this conjugate base. Since this conjugate base is more stable, so the HCO carbonyl whole 4 is more bronze-state acid than the HCO PME3 whole 4. So in the statement, HCO CO whole 4 is less bronze-state acidic than HCO PME3. So this statement is wrong, or you can say incorrect. H cobalt CO whole 4 is more bronze-state acid than HCO PME3 whole 4. We just saw, and we also discussed details that the conjugate base of this organometallic complex is more stable, that's why it's more bronze-state acidic than the conjugate base of this. So we can say that this one organometallic complex is more bronze-state acidic than this organometallic complex 2. So I think you got the point what I was trying to say. So yeah, now let's move to the next statement. So that is about the geometry of nickel tetracyano 4 minus is tetrahedral rather than square planar. So let's see that. So we all know that NiCl4 2 minus, this is nickel 2 means D8 system tetrahedral. We all know that NiCl4 2 minus, so nickel 2 D8 system tetrahedral, and NiCN4 2 minus, it is also a D8 system, but it's assume square planar geometry. So square planar geometry. So in case of this D8 system, when there is a strong field ligand like Cn, so it's prefer square planar geometry rather than tetrahedral geometry, because in square planar geometry the CFSE become more negative. So in presence of a strong field ligand, here chloride is weak field ligand, here just we change the ligand Cn is strong field ligand. So in presence of this strong field ligand, that del O become more. Del O become more means the separation between dx square minus y square and dxy become more. That's why in square planar geometry that that 2 electron in D8 system comes to the come to the lower orbital, that is dxy, yeah, dxy in that case. So that's why it will gain some extra crystal field stabilization energy. We all know these two things. So nickel Cl4 12 minus di tetrahedral, in case of strong field ligand, same nickel complex become square planar geometry, because in square planar geometry the CFSC become more negative. It will get extra stability, extra crystal field stabilization energy in square planar geometry. We all know from our undergraduate studies these things, we all know. Now come to the point. The given complex is given as nickel tetracyano 4 minus. So nickel tetracyano 4 minus means this is the D10 system. Please keep in mind this thing: NiCl4 2 minus, D8 system tetrahedral, NiCN4 2 minus. Just in presence of strong field ligand, we all know D8 system, it is also D8 system become square planar geometry, because in this case CFSC become more negative. Now come to the main complex that was given in NiCN4 4 minus. This is a D10 system. So strong field ligand is there, 4 minus D10 system. By seeing first time, one can assume that yeah, this is D10 system. They will forget that D10 system. They just think that yeah, CN ligand is there, means strong field ligand is there, so it will and 4 ligand is there, so it will prefer square planar geometry rather than tetrahedral geometry. But that is not the case. So let's see, let's discuss the questions in details. So NiCN4 4 minus is D10 system, and we all know D10 and D0 system, there is no crystal field stabilization energy. So D10 system, there is no CFSC, means crystal field stabilization energy is 0. So since there is in the previous two cases D8 system, there is some crystal field stabilization energy, that's why in presence of strong field ligand, this complex prefer tetrahedral geometry, or just we change the ligand from weak field to strong field, it's prefer square planar geometry. But still in this complex strong field ligand is there, but it is D10 system. There is no crystal field stabilization for this complex. That's why for this case stability will be decided by the steric factor. Since there is no crystal field stabilization energy, there is no questions for weak field strong field ligand. Since there is no crystal field stabilization energy at all, because D10 system, if we calculate the crystal field stabilization energy, CFSC value for D10 system, it will become 0. So there is no questions for weak field strong field ligand. It is nickel tetracyano 4 minus complex, strong field ligand is there, but the system is D10 system. So nickel in its D10 configurations. So D10 means there is no CFSC, there is no crystal field stabilization energy. For this type of complex, stability decided by the steric factor. If we draw the square planar geometry, see, this is the square planar geometry, this is the tetrahedral geometry. In square planar geometry, the NiCN bond is 90 degree. This all CN bond is 90 degree. So since these bonds, these two CNs are connected by the nickel center via with the angle of 90 degree, there is some steric clouding or steric repulsion between these two CN group. In tetrahedral geometry, the bond angle between this CNC is around 109. So in this case, less steric repulsion between the two CN group. In square planar geometry, there is a moderate amount of steric repulsion between the CN ligand because of the bond angle. In this case, bond angle is 90 degree. The nickel CN bond angle is 90 degree. In this case, nickel CN bond angle is 109, that is 19 degree more than the square planar geometry. So since in tetrahedral geometry the steric repulsion or steric crowding is less, that's why this complex will always prefer tetrahedral geometry rather than square planar geometry. Again I am repeating you that D10 system, we have to consider the strong field, weak field ligand, square planar, tetrahedral geometry. In case of a d electronic configuration where there is some CFSC value. In nickel tetracyano complex there is no CN and no CFSC value. This is a D10 system, that's why there is no CFSC. CFSC is 0, that's why we have to consider the stability by the steric factor. So in this case the stability of this complex decided by the steric factor. Since in square planar geometry there is more steric repulsion between the ligands than the tetrahedral geometry, so this complex will always prefer or always assumes this tetrahedral geometry rather than square planar geometry. So please keep in mind, always keep in mind, this nickel tetracyano 4 minus D10 system will always prefer tetrahedral geometry. Since this bond angle is 109 degree, there is less steric repulsion between the CCN ligand than the square planar geometry where the bond angle is 90 degree between the CN nickel CN. So some more steric repulsion or steric crowding is in the square planar geometry. So this complex always prefer tetrahedral geometry rather than square planar geometry to release the steric repulsion between the ligand. So in the statement the geometry of nickel tetracyano is tetrahedral rather than square planar. So statement 3 is also correct statement. So we saw details, we have discussed details that the statement 1 is correct, statement 2 is incorrect, wrong, statement 3 is also correct. So among these three statements, statement 1 and statement 3 are correct, statement 2 is incorrect. So I hope guys you all understood this discussions, this points we just discussed. If you have still any doubt, please comment in the comment box, then we will try to clear your doubt. So yeah, thank you for watching, thank you for your support. So yeah, stay tuned because we will upload lots of conceptual questions in our upcoming videos. So yeah, stay safe, stay healthy, bye, thank you again.